John Jasper. I want to take this time to welcome you for another video still under fluid mechanics. So today we're going to talk about a property under fluid mechanics, which is viscosity. Last time in our first video, we talked about some properties under fluid mechanics. We talked about specific weight, we talked about specific gravity, specific volume, very many properties. But today, the first video we're going to choose one of the properties, which is viscosity. We're going to talk about it in details. What is viscosity? And what do you know more about viscosity? Then probably we shall do more examples under properties of fluids. So, viscosity is a property of a fluid which offers internal resistance of a fluid in motion. So, that resistance there is what we call viscosity in a fluid. So, we are going to illustrate viscosity very well using two parallel plates. So, we are going to consider two parallel plates A and B. So, the two parallel plates A and B, we are going to assume that these plates are separated by distance L. So, again, I'm going to assume that the plate is down B is not moving, is stationary, it's not moving. That means the velocity, this U stands for velocity. That means the velocity U of this plate which is down is 0. And distance x. X stands for distance, U stands for velocity. Now, as we move up to by distance L to plate B, it will be x. Distance x will be equals to what? L. Then the velocity we are going to assume is v, because plate A rather is moving with some velocity v, but plate B is stationary. That means its U is what? 0. So we are going to draw a velocity profile for this. So for at B, x is 0 and U is 0. Why? Because the plate is what? Stationary. So as we move up, the velocity will be increasing. Will be increasing up to plate A. So that increase will create for us what we call a velocity profile. Here is 0, but when it comes inside here it's maximum. You get? So here velocity is what? Maximum. Here the velocity is what? 0. So what we call this is called the velocity profile. This one is called the what? Velocity profile. Here. So now, since this plate here, this plate A is moving with some force F, that means there will be a shear stress created. And the shear stress, by definition, is this. You must have very well, shear stress. Shear stress, which is given by the symbol tau, this symbol here, is given by the ratio of force to the area. This shear stress, this one formula of shear stress, let me put as equation star. Shear stress tau, which is expressed in these parallel plates due to the force, is given by force over area. This formula is very important for calculation purposes. Please master it. Then also, we are going to consider another formula under shear stress. So shear stress also is given by this symbol times du dy. So let me define the terms. Let me call the equation what? Double star. This equation is going to be used so much for the calculation purposes. So when it comes to tau is called shear stress. Then this mu is called dynamic viscosity. This mu is called dynamic viscosity, or sometimes people call it coefficient of viscosity. So you can say this mu is called what? The coefficient of viscosity, and the value is constant. The value can be given, also I can ask to calculate it, but it's a constant. Then the u dy is what we call the rate of shear strain. The u dy is called the rate of shear strain, or you can call it the velocity profile. So that means where also you can say where du dy is the velocity gradient. You get? So du dy is velocity gradient or the rate of shear strain. So this relationship brings us to a law. And the law is called the Newton's law of viscosity. This one brings us to a law called the Newton's law of viscosity. What does it state? Newton's law of viscosity states a law is a law. You must state and not change anything, because the law remains a law. So the Newton's law of viscosity states that the shear stress tau acting on the fluid is directly proportional to the rate to the rate of shear strain. The shear stress is then proportional to the rate of shear strain. Or you can simply say the shear stress acting on the fluid layers is then proportional to the velocity gradient, because this one is definitely constant, like K. This one is a constant of proportionality. So what I'm meaning, our tau is direct proportional to du dy. This is what we call Newton's law of viscosity. The shear stress is proportional to the velocity gradient. So, and fluids that obey that law, they are called Newtonian fluids. So they may ask you sometime that what are the Newtonian fluids? They are fluids which obey the Newton's law of viscosity. Then maybe lastly, for the last formula under viscosity, we're going to talk about kinematic viscosity. The last formula is called kinematic viscosity. And kinematic viscosity is given by mu over the density. And mu is saying is what? Mu is dynamic viscosity. This means dynamic viscosity. This density is just a density, can be density of water or the substance which is used. So thank you very much, and thank you for watching this video on viscosity. And let's meet next time for the properties of fluids examples. Thank you very much. Okay, as we're going to meet next time for another video, I know we shall do more examples for the fluid, but for today's purpose, let me just do for you one number for the fluid, just to give you an insight on what I'm discussing. Because all along I've been talking about theories. So now we're going to talk about now calculation. Let me just give an example for today. Then next time we shall do more examples for the fluids. Then we'll go to another topic. So the first example we're going to talk about is this. It is saying determine the dynamic viscosity mu of an oil which with a dynamic viscosity, that one there, and relative density also equal to this. So that means they want what? Mu. Let's summarize the question. They're saying they want dynamic viscosity mu. Just call it mu. We don't know it. But they're saying they've given us what? The kinematic viscosity. Let's summarize. They've given us what? Kinematic viscosity. And the value is, this value it is 3.352 times 10 power negative 5 meters per second. That is it. That is kinematic viscosity. And the relative density I told you is the same as specific gravity and the properties of fluid. So our relative density or specific gravity is the same as that. So you can say relative density. Relative density, because the same as specific gravity, is given by 0.88. So that is our relative density. Let's calculate the same way we want dynamic viscosity. So we are going to pick some formulas which relate them to viscosity and kinematic viscosity. So I'm going to say using follow it very well. Kinematic viscosity is given by we say the same as dynamic viscosity mu. Mu is a what? Dynamic viscosity divided by the density. Density. And for this case, our density is oil. It's not water. It's density of oil. So here is going to be density of oil. Do we know kinematic viscosity? Yes. The value is what? This 3.352 times 10 power 95. So you can substitute here. So it's going to be 3.35 times 10 power, there's a 2 here, times 10 power negative 5, the same as mu divided by density of oil. Let's call it what? 1. So what do you want the question? You want mu, which is dynamic viscosity. So but you have to get what? Density of oil first. But density of oil can get it from another relationship because you know relative density. You can say but relative density the same as density of a substance, and of which the substance is oil. It's going to be density of a substance, follow very well, over density of pure water. So density of substance is going to be like oil, our density of pure water. So what is relative density? The value is given, the value is 0.88. So it's going to be 0.88, the same as density of oil is what we're looking for. It's going to be density of oil divided by density of water. We know is standard. It is 1,000 kilogram per meters cubed. So you can get that. You can cross multiply and we get density of oil. So as we continue, let's get our density of oil. So density of oil will be equals to, it's going to be equals to 0.88 times 1 1000. So it's like simple terms going to be 88 over 100 times 1000. We cancel this and that. We shall be having 88 that kilogram per meters cube. That's the density of oil. That's the unit. So you can pick this density of oil and put it inside this formula here, equation 1. So you can say substitute in equation 1. Substitute in equation 1. So I'm going to say from equation 1, which is 3.352, follow very well, times 10 to the power negative 5, the same as mu is what I'm looking for. Mu over density of oil we have got is this. It is 880. So then now you can now cross multiply. You can now say our dynamic viscosity. Our dynamic viscosity is going to be equal to that times 3.352 times 10 power minus 5. We get. So I think it's going to be mu, which is going to be equals to. So you can compute this and get this answer. Let's multiply this by that, then get that answer. So dynamic viscosity can be equals to the unit can be Pascal seconds. Pascal seconds or other units like Newton per meter squared. So thank you very much for attending with me. And I want to say that the next video I'm going to do some more numbers under properties of fluids. Then we go to other topics like hydrostatics and dynamics. Thank you very much for listening. Please don't forget to subscribe, like my videos, comment below. Thank you very much and share my videos. Thank you very much. My name is Sirimen's Don Jasper. May God bless you.